He is a lecturer in geotechnical engineering at UNSW Sydney, which is ranked 19th globally by QS World University Rankings. He has an extensive expertise in soil dynamics, geotechnical earthquake engineering, and blast loading on geotechnical structures. He has significant experience in physical model testings of various geotechnical structures and has led several research projects involving experimental, numerical, and analytical study on different geostructures. His primary focus is on establishing performance-based seismic design guidelines for different geotechnical structures. With a unique combination of experience in engineering, consultancy, research, and academic teaching, Dr. Rohit effectively bridges the gap between the academy and the industry. So let me once again welcome to Dr. Rohit Tiwari and hand over the stage to him for his presentation. Very warm welcome to you, sir. I hope it is different timelines with you, and it is quite okay with you to be with us at this order also.
That's all good, not a problem. I hope I'm audible to you.
Yes, sir. Yes, sir. You are very much audible.
Okay, so I will just share my screen and.
Correct, sir.
So can you see my screen now?
Not now, sir.
Listen, I will try again.
You can go to present now tab, which is the up arrow sign. Yes, now it is very much visible.
So should I start now?
Yes, sir, sure.
Okay, hello everyone. So I think I've been already introduced by the host, Setan Gupta, and just giving a little bit of idea about my research and what I'm doing here at UNSW. So I'm basically from India, of course, and moved to Australia in 2016 to pursue my doctoral from University of Melbourne. And I did my PhD in the area of geotechnical earthquake engineering and did extensive research work on understanding the seismic performance of different earth retaining structures. So the research I will be presenting today is a part of my doctoral research, and then from last 4 years. So I finished my PhD in 2020, and then I worked in different engineering consultancies in Australia for around 1 year. And then before joining UNSW, I was working with the WSP Code in Brisbane, where we were looking into the stability of a very deep open pit mine in Papua New Guinea. And then 2021, I joined UNSW, and since then I'm working here as a lecturer. And my primary focus of research at UNSW is understanding the seismic performance of mine tailings. So I will be discussing a lot about our testing program here at UNSW at the University of Melbourne as well. And see, hope you like it, okay? So let me just start my session. So this is my first slide. I always like to start my presentation with acknowledging the land, that's the culture in Australia. So first of all, I would like to acknowledge our original owner, the traditional custodian and original owner of the land, Gadigal people, at which our beautiful campus of University of New South Wales is built up in Kensington, Sydney.
Thank you for including the slide.
As we are also having a very great connection with and deep connection with India, so I would also like to take this opportunity to remember every freedom fighter who participated and gave the ultimate sacrifice for the independence and building up this beautiful nation, India. So now I will start my slide. So this is my outline. So I will be talking a lot about geotechnical earthquake engineering and especially earthquake loading in geotechnical structures, how the loading can be disastrous to different form of geotechnical structures, how earthquakes are coming and acting on the geotechnical structures, and why the destructions or the collapse of geotechnical structures are happening. Then we will move towards understanding the role of the physical models and understanding or to study their behavior and try to compare it with the prototype, which is actually a full scale model. So what's the importance of these physical models and how much they are capable of to replicate the seismic performance or the earthquake response behavior of uh, a prototype or a large scale geotechnical structures. And then I will be talking a lot about our new biaxial checking table, which is our own design. And there is a reason why I included this to highlight that how everyone can design their own equipment. And then by doing this, you can save almost 50 to 70% of the cost, uh, which is really important in terms of course, the money, and then getting an idea of your experiment setup and its capabilities rather than buying it from a commercial supplier. And then I will be talking a lot about shaking table testing on the earth embankments, which we are doing here at UNSW using this new shake table. And then the shaking table testing on retaining wall models in University of Melbourne. And then at the end, we'll try to bring the whole story or try to summarize it that how we can use this understanding which we can build from experimental geotechnical engineering. It is just not about the shaking table testing. It is more about how you can use the result of any study to bridges the gap between academia and industry, and then use the same information to teach or train our future engineers who are doing their undergrad or masters in civil engineering discipline. So I'll start this by showing you some interesting photographs of different retaining structures for the audience who are not very familiar with the retaining structures or retaining walls. So retaining structures or retaining walls, they can be a retaining wall like this highway. Okay, so there's a filling there, and then in order to support the filling, you have to construct a retaining wall. And that's how it looks like. So you have a stem, the cantilever retaining wall, can be gravity retaining wall. There are different kind of retaining walls are available. And then you fill it with a backfill. Generally, it has to be a cohesionless backfill so that water should not be retained inside the soil and then water can seep through. And it has a better frictional property so that you're getting a higher shear strength from the soil, and then it will give you a high stability of the retaining wall. Now, this is another kind of retaining structures where you are seeing here is a bridge abutment. Everyone, I'm pretty sure, have traveled through the bridges nowadays. They are one of the major part of any modern infrastructure system. And so the bridge abutment is also kind of retaining structures where the abutment is retaining the backfill behind it, similar to this. But instead of retaining wall, now it's supporting also one girder, so there will be a reaction from this side as well. Now, this is another form of retaining structures. So it can be a basement wall, or it can be a sheet pile wall supporting the harbor structures, or a diaphragm wall. Now, this is again a harbor infrastructure where you are seeing a quay wall, and because of the high water table and having sand below it, when they are constructed in harbor medium, they are subjected to chances of liquefaction, where your ground loses almost all its strength and soil started behaving like a liquid. And in India and in Japan in 2021, no, not 21, sorry, 2001 earthquake in Boja, I think, these walls were reported getting damaged because of the liquefaction. And even in Kobe earthquake in Japan, there was a report of getting damaging of this wall because of the liquefaction. This is another kind of retaining structures where you have a traditional retaining wall, but because of the low bearing capacity of the ground below it, you need to transfer all the road to the rock below it. And so this one is like a rock socketed pile, and there is a backfill behind it, and it's supporting a railway line. But it could be a roadway or any other thing. Just I'm trying to show you different applications of retaining structures. And then, because I will be also talking about the mining embankments or tailing dams. So this is a photograph of a tailing dam. So people who are not familiar, what are tailing dams? So I'll just give you some introduction of it. So when you do the mining and you have to extract the ore from the mine, it's like rocks. and then you crush them, make a slurry or powder, and then mix it with the water, extract all the minerals. It could be a gold, copper, iron, and you take up that mineral out of it. And then the leftover is like a form of slurry. So whatever you are seeing here, and then you just dump it to a facility. We call it a tailing dam. Now, over the period, depending on how you are constructing your dam, it could be upstream or downstream method. Um, you will be getting a very large height of embankment, might be from 30 meters to 100 meters height, very loose material, uh, and very weak material. And because of the water table is presented there, so and they are subjected to the earthquake, there already have some failures in the past where the tailing dam failed, and it's a very significant environmental disaster as well as a disaster for the human being. So if you see this photograph, and this is not from India, I think, but even in India, when we are looking at Indian, especially southern part of India, you have lots of tailing storage facilities in India, and this is like a disaster situation when you have in the vicinity of the dam, you have a massive population living by. So in the case of failure of this tailing dam, this won't be this won't be just a natural or environmental disaster. It will be a disaster to this population and disasters to any river which will be in the vicinity of this facility because of the high contamination of minerals and the heavy metals presented in that water. So there are reports in Australia and various parts of the world, in Brazil, Chile, where this tailing dam failure occurred in the past, and it resulted in a loss of lives as well as the long-term contamination of the land. So we have to make sure that these facilities needs to be at least serviceable or should not get collapsed during a design level seismic event. So we'll be showing you. I will be showing you what we are doing here. So in terms of shaking table tests on these loose materials, which is known as tailings. Now, if you see here, these are some photographs just to show you the how important these structures are and how vulnerable they are when they are subjected to the earthquake loading. So this is a failure of retaining structures, and because of that, you can see the whole railway line got blocked. And there's again the slope stability problem because of earthquake. Slopes might become unstable and then it can flush. Another problem in, I think in Japan, Kobe 1995 earthquake, and you can see retaining structures got failed, and this is a track, and there is a train park on top of it. Again, the failure of earth retaining structures in a railway station. This is a photograph which has been taken in 1923 from Great Kanto earthquake in Japan, and you can see the failure of a retaining wall, and there was a railway line. So I'm not sure whether you can see this. There was a railway line which was passing through this side and then got damaged because of the slip. Then in Chile, in 2010, there was an earthquake, and because of that, you can see the failure of this bridge abutment. So there used to be a bridge here, and because of the earthquake, there was excessive rotation and the sliding of this bridge abutment, and then the girders, they just collapse. But of course, they are not here. They might have to move it just to clear the highway. Now, this is in 2001 Bhuj earthquake, which was one of the disastrous earthquake in the history of modern India. And I think it was 26 Jan. I was a kid in school that day when this earthquake occurred in morning, and lots of people lost their life. I'm not sure, but the death toll is around 10,000 people. And this is a photograph, aerial photograph of a sheet pile wall. So it's like a sheet pile wall, and because of the liquefaction, the whole land got submerged when it turned out to be a liquid, and the sheet pile get damaged because of that. This photograph has been taken from 2009 Italy earthquake, where you can see the failure of earth retaining structures. It is not a very long or large wall, but it still got failed. This is very unusual photograph captured in Loma Prieta earthquake, and you can see the peak on acceleration, which is quite high, 1G. and you can see the crack in the wall, which is not very common because earth retaining structures are very massive. So the failure of these structures shall generally occur much before the failure of the concrete or the reinforcement supporting the concrete. The failure usually occur like this. So you have earthquake, there will be a rotation of the wall and the sliding of the wall. And once it happens, the backfill just falls on the top of it, and then there will be a complete disaster. So that is a failure of earth retaining structure where we are not interested to see or investigate this kind of failure of concrete or the reinforcement in terms of retaining walls, because you will be getting the complete failure much before then concrete will get the cracks in it. There's another environmental disaster occurred in Santa Barbara in California, 1925. And you can see the failure of a dam. So this is before earthquake and this is after the earthquake. Now, before moving forward in this structural aspects of the performance of earth structures when they are subjected to the earthquake, I just wanted to make you a little bit more familiar with how this earthquake loading is acting on a retaining wall. So this is a freestanding wall which we can slide on its base, and then it's having this backfill soil behind it. So when the earthquake comes, this wall may slide. Of course, not this much. This looks a little bit dramatic, but just to make it more fancy. And it can also rotate. So the failure can happen because of the rotation and the displacement of the wall. Once the wall displaces to a very small amount, it could be 0.2% of the height of the wall, there's a formation of the active failure wedge behind the wall. So if you're familiar with this Rankine earth pressure theory from your undergrad, you might be able to correlate it. Now, this is the earth pressure acting on a retaining wall in a rest condition. So there is no earthquake at this stage, and this is the weight of the wall, weight of the soil. And you design the wall for sliding, overturning using the different earth pressure theories. And this is the active failure wedge. And because of that, you are getting the failure plane behind the wall. So the total earth pressure which is acting on this wall in active state is the pressure will be K comma H, and then area of this triangle will be the force acting at a height of 1/3 to the complete wall height. And then you check the factor of safety of this wall, and they're subjected to the sliding on overturning. This is a very classical undergrad problem. And when the earthquake comes, then this force changes because of the earthquake. There will be inertial component acting from the soil to the wall, and there will be a rotation and the sliding and the formation of the active failure plane behind the wall. So in the terms of earthquake, there are inertial forces acting along with this vertical forces from the soil and the self-weight of the wall. And because of those inertial forces, the wall will get an additional earth pressure from the backfill, which will resulting in the displacement and the rotation of the wall. So this is again the photograph captured showing the damage of to the bridge abutment, the settlement of the soil, and the rotation of the abutment. And it not only create the damage to this structural part of the bridge, it can also initiate excessive serviceability failure because of the higher settlement of the road or the approach road, which is connecting this bridge to this highway. And once it happens, you can't use the bridge anymore. So as I just discussed about the role of different forces in the retaining wall, when it is subjected to the earthquake because of the inertial component, so there will be inertial force acting in the lateral direction during an earthquake. Now, if you remember from the previous slides, so this is the active failure plane, not the active failure plane, this is the total active earth pressure acting on the wall because of the Rankine active lateral earth pressure coefficient. And when the earthquake occurs, what happens is this failure plane or the earth pressure envelope basically, it got enlarged. And instead of the static component of the lateral earth pressure coefficient in active state, you are taking a dynamic component of the lateral earth pressure in the seismic state. And if you can follow the same approach, if you know somehow what is this KAE value, then the design is similar to the static case. And you just need to find out the total forces, which is the area of this triangle. And then the theory says it will act in a height of h by 2, which might be controversial, and I will discuss that. So assumption says, similar to the static case, the dynamic earth pressure will also be linear, but that's not the reality. It is non-linear, and I will show you that. These two guys, they tried to modify the Coulomb earth pressure theory in order to find out if you can come up with similar arrangement, just the linear variation of the earth pressure, similar to what you can get it from the Rankine or Coulomb earth pressure, lateral earth pressure coefficient. If you can modify the Coulomb earth pressure theory, and you can estimate or at least idealize the similar behavior for your design of retaining wall when subjected to the seismic loading. And they gave equation in 1929, which is still valid in European code, Indian code, OSTO, and even in Australian codes. And then the process is same. Once you know the additional earth pressure, you can find out the moment for the thrust or the increased component. You just add it with the static earth pressure, and then find out the factor of safety in sliding and overturning. Okay, so the question is still the same, whether the earth pressure is linear during earthquake or not. And so when you calculate this KAE, if you can open this or can read about more about this if when we have some time. So if you find the equation to estimate this KAE, it does not have a timing component in it. So you will be designing your earth retaining structure for this increased seismic pressure for his whole life. And in most of the cases, there are very few chances that a retaining wall will be subjected to more than 1 or 2 times to the earthquake. So the question is still the same, whether you should design a structure for this enlarged earth pressure or should be reducing it. So the codes sometimes they say you may be allowed to reduce it by 50%, depending on if you are allowing some displacement of the wall. So if you if you are allowing the displacement of the wall, you may be able to reduce this KAE by 50%. But the problem is how you will quantify that how much wall will displace during an earthquake. And that was the main motivation of the research, that quantification of the moment of the wall during an earthquake. So how we are going to study the behavior of the walls during an earthquake is you can either do a computer simulation or you can do a physical model testing. Doing the computer simulation looks easy and lucrative, but if you guys will search about the neck hole highway failure in Singapore, you will be amazed of seeing how much wrong results the computer software can give you. And it could be very much um, underestimated or overestimation of the strength, and you won't have any clue that what is happening. Now, if you go, there are another option is you just go and validate first your work with the already published experimental work. There might be an option, but in most of the cases, the experimental work, when we were looking into it, they were reporting the maximum values of the displacement, that pressure along the height of the wall. None of them were talking about the timing, which is the complete time history of the displacement of the wall or the earth pressure. And this gives us a little bit of motivation, like we should also start looking into doing our own tests in order to get a complete picture and then develop our own numerical model to estimate or simulate at least the seismic response of the retaining structures. So we have to come up with some idea to scale down the model behavior, which is in this case a retaining wall scale down model. And you have to follow these analysis, which in the 1G environment will assume the same material, same acceleration, etc. scaling of time. But the problem with this kind of analysis is it needs a centrifuge, or you have to play with the acceleration. So I'm sure people are familiar with the centrifuge. If you have went to a blood bank or have donated blood, or even go for a blood test, you might have been seeing where they are keeping your samples. So that is a kind of centrifuge which just rotate, but this is a kind of geotechnical centrifuge in California. And this supports the geotechnical model here, and then you can play with the rotation, and then it changes the value of G, and you can simulate any condition inside this. But the problem with this is in India, there's only one centrifuge. As far as I'm aware, before leaving India, there was only one centrifuge in IIT Bombay or somewhere nearby, and everyone is looking to use for it. But the problem is, once you do the experiment, you can't just finish the research based on one experiment. You have to do many experiments. So half of the experiment, you will be missing something. And then you realize, okay, this is wrong, and then do it again. But if there is only one centrifuge in the country and everyone is just looking to use it, there is no chance you will be getting it more often if you are doing any mistakes. So there are limitations of the centrifuge. First, they are expensive, and then second, limited availability. So not popular. That's the main reason. It's not very popular in parts of the world, but they are really useful. So there is only one centrifuge in Western Australia, and in the entire Australia, and that is also not this much big. It's very small. So there is one alternative of this centrifuge testing. You can go for the physical model testing in 1G environment. So this is a 1G environment where you're not changing, you cannot even change the gravity. So you have to be with the gravity, but you can play with the equations in these theorems. And then when you do them, you can come up with some sacrifice. So you won't be able to get very true response of the model, but you will be able to get a really good understanding of the material behavior, the deformation of the scaled down model, and then you can use the same model for your numerical analysis to compare and learn how to do a correct numerical modeling. Now, if you can see here, I don't know, I just made my camera is not working. I hope you can see me also.
Now we can see you, sir.
Okay, sorry. I just realized it's not working. Sorry for that. Now you can. So if you talk about this physical models, then the next question comes is, if you are using a physical model or any type of loading, it can be a static loading, it can be a dynamic loading, but the $1,000,000 question is, what's their capability? Are they able to replicate the realistic performance of the actual big model or not? And that was the first learning from me in year 2016 when I started looking this first time. So if you follow this scale down simulation analysis, and this is an example of the wall. So if you can see, the height of the wall is around 3.6 meters, and the thickness of the stem wall is 0.35 meters. And if you do those scale down modeling, do the analysis, and use a computer model to do a scale down model of this. And as I told you, computer model is a black box. It does not care about anything. So you can do any scale down in the computer model, which is not feasible in a real world. But the computer model can do that for you. Okay. And if you do that, just to see whether this approach is working or not, so you can follow this approach. So you do the scale down model. So this is a tiny model which represents this big model in a computer software. And it looks something like this. So it is a 10 scale down model, and everything is divided by 10, these dimensions. Okay. So this is 0.3625 now, 0.035 meter. And that's, you did the same thing for the properties of the materials. It's a wall, concrete wall, and background. And once you do that, follow the scale down modeling, do the same material modeling based on the scaling laws, and this behavior you will get. So this is a relative displacement. So you You have relative displacement. What does it mean? It's the displacement at the top and you minus the displacement at the base. So subtract the displacement at the base from the top and you get the relative displacement. And the result looks very promising. So if you see this is a very dynamic pulse, and this is a real earthquake recorded in Iran. And that's a huge displacement of 250 millimeter. And both the models, so it's a scale program model is this, the scale law models is values are here, and this is the comparison looks really lucrative. This means the scale down models may be able to replicate the realistic performance of the program model. But one thing I just want to make clear, the scale down model will not show you this 30 millimeter displacement. Instead, it will show you 3 millimeter displacement. And the same thing with the time scale, because the scale down model, if you do, you have to squeeze down everything. You have to squeeze down the time, you have to squeeze down the dimension. So once you do that, you will be getting, response will be like this, but it will be a squeezed domain. So the amplitude will be 3 millimeters somewhere, and this will be around square root of the time, whatever time is here. So then you have to again enlarge it by multiplying with those same scaling relations and then superimpose the result. And this is the final outcome of the result, which looks good. And it means the scalar models are able to replicate the behavior of the prototype model, depending on you are scaling them properly and then following all the similitude criteria. Now, the next step was how you're going to cast the model of that. And then we tried to relax the materials, same material assumptions, because of, as I told you in the previous photographs, that the materials in the arsenal structures, the stiffness of the structure is quite high. And in this case, if the structure's stiffness is very high, it will fail much before the failure of the concrete because of the excessive rotation displacement. And we tried to, make a different material, make a class, or maybe the manufacture our scale down model using a very different material, but the scaling was satisfying. The material was like a plastic sheet, and you can read the paper. I will be showing you the citation later on. And then we did the experimental testing and tried to analyze the result. So this is about the physical modeling. Now we will move now to our novel bike shell shaking table, and then some more results of the physical models will be coming in later slides. So the next step is, now you have a physical model, you did the scale down modeling. Now how you're going to excite the model, and you need a machine for it, because the accuracy of the models is completely dependent on how accurately you are analyzing their response. So if you can see, this is a shaking table which we have designed in-house at UNSW under ARC Future Fellowship Project. And the table is a bike shell shaking table. What does it mean? So the table can go in horizontal direction and vertical direction simultaneously. So that means it's a bike shell shaking table. It is a novel design because the design looks something like this. So it has two arms. So this is called long scissor arm and short scissor arm. And it follows a scissor mechanism. So if you have used a scissor, you can relate that scissor mechanism with this arm, and I will show you while this table is in operation, and then you can correlate it very well. And two actuators placed in it, and there is a rigid base and the red blocks where this base of the table, upper base and lower base, they move, and you can simulate or achieve the horizontal vertical displacement of the table. So these are the table dimensions, 1.5, 1.5, but you can enlarge it by putting a metal sheet on the top of it. And the total payload capacity for this table is 3000 kg. But if you want to get more of this, you can just increase the diameter of the actuators and the size of the hydraulic oil supply. And it can take around 0.9 for the earthquake pulses, 0.6G in horizontal direction and 0.4G in the vertical direction. These are the movement range for the table, which is very good because of the scale down models. You have to apply scale down pulse. So this is okay, the horizontal and vertical movement capacity. Let's see how this table works. I have to, I think. So you can see the movement of the table. So two actuators, this is the lower base, upper base, and this is the arms. They are trying to move the table in horizontal direction, the base, lower base, and the upper base is trying to move the table in the vertical direction. So let's see the cost comparison. So if you want to buy a table from any American suppliers, most of them, they are European or American. So uniaxial shaking table with the 3000 kg of load capability, just 1 degree of freedom, so it can only go horizontal. It costs around 5.5 crores Indian rupees. It's around 850,000 Australian dollars. Now, if you are going to buy a hexapod shaking table, which is a newly arrived table from American players, if it's a 2,000 ton capacity, the cost is around 18 crores Indian rupees. But this novel biaxial shaking table, we have achieved this in around 7 crore Indian rupees. Given that the fact that 10% of the table cost is for the manufacturer or the labor for the foundations, because it has to build upon a very strong floor, which is around 1.5 meter deep, because of the machine foundations are quite high. So this table can go up to, I think they are saying 50 hertz, but if I take that to 20 hertz, the whole building shakes at UNSW. So I never went more than 20 hertz. So this is about the table design and the cost comparison. We also tried to understand the capability of the table using the finite element models. And this is a actual isometric diagram of the table, which is this one. And this is a two-dimensional equivalent finite element model of the same table. And these are the fundamental mode of frequency quite close. And once we tried to simulate that, it took some time, but we come up with a really good agreement between the finite element model and the shaking table results. So this is a biaxial movement simulation using computer model, and this is the actual shaking table moment. And this is the result of the finite element simulation and the shaking table experiment. So they are quite good agreement, despite the fact that in some way we are going for a quite high frequencies, 10 hertz. With the 20 hertz, it was showing a very good agreement. Now, the next step is, because it's a biaxial shaking table and it uses Caesar mechanism, but the problem is we are going to test the geotechnical model, and the geotechnical models in the field, they are subjected to the free field condition. Then how are you going to test that? And this is a new, our own design laminated shear stack, which is having these springs at the boundaries. So when you put the model in it, so right now we are doing the testing on the tailings, and these are the instrument. And then when you put it and you put the whole thing on the top of the table, I will show a video after this slide, and you can simulate the free field response of the soil. So the reflections from the boundaries will be limited, and then you get a free field response at the center of the model here. And in one test, it takes us around 2 to 3 weeks of the preparation. Today I wasted 4 hours in the lab to make the few instruments working. No success. So that's why it takes 2 to 3 times just to prepare for one test. It takes around $6,000 to $8,000 for one test. And once you come up with that, and I will show you how you can get a really good research output based on this shaking table test. So this is Center for Infrastructure Engineering and Safety, CIS, at UNSW New South Wales. And I will show you a typical test which we are doing using this table. The instrument side it. So each shaking table test needs around 220 different wires needs to be accurately connected to the instruments. And otherwise you'll miss a result if you miss that. So this is the warming up. So hydraulics needs to be warm up, ensure that they will be working throughout the test properly. Then you need a crane to lift up the model, put it on the table. But now we have our own crane in the lab, so we don't need to hire it. They're quite expensive in Australia. It's around 10,000 Indian rupees for 1 hour So this is the team working for the experiments. All the wires needs to be first untangled and connected to the different data loggers. So now we have already set up all the things. Wires are now connected. So that's the main controller of the table. This is the acceleration logger. That's the logger for the piezometers, which we measure the pore water pressure inside the soil. And these are the lasers trying to read the displacement of different laminates. And now I started a test. So this is the input pulse, and you read the pore pressure. So as soon as this line hit the zero effective stress, it means the liquefaction. Soil already lost all the strength. And we keep increasing the excitation. So this is 0.9 G, which is quite a lot. So you can see the movement of the laminas. So that's about the shake table test. I'll quickly try to move into the final slides because I think I'm extending the time limit. So this is the result. So this is the liquefaction. You have time versus acceleration, a different ground acceleration at different heights in the soil. And if you can see the green one, which is at the upper layer, so you can see the liquefaction in the upper layer. So where there is a discontinuity in the acceleration, there's a liquefaction. Here, no liquefaction because of the low peak ground acceleration. High peak ground acceleration, you can see the liquefaction in the upper layer of the soils, and then it convey to the bottom and the middle layer as well. This is the displacement of the laminas. So the take-home lesson is the soil strength mobilization inside the shear strike is not linear. It mobilizes strength along the laminar edge, of course, because they are trying to push the soil along the aluminum frame. But the good finding was the movement of the laminas or along the strings are non-linear. And this work is in review right now with the soil dynamics. So this is again on the retaining walls, or the embankment now, and that's even a smaller model published in Soil Dynamics of Engineering. And you can see that's the container, and then we can see back from different layers. And these are the lasers. These are different instruments, and then press drop we used for different layers, dynamic compaction to make them flat behind the wall and do the maximum dry density of the soil. And then we did the excitation. The test has been conducted with different pulses, and I can show you that this one is a pulse test. So pulse tests are it's like a high velocity pulse. So you go from 0 to maximum displacement in 0.1 to 5 seconds using the shaker, and then leave the system to vibrate freely. So this is the loading phase or forced vibration phase. This is the free vibration phase. So once you leave the system here, it will vibrate freely, and you capture the record here, acceleration or displacement of the wall or acceleration in the soil. And then you do the frequency domain analysis on it to get the natural frequencies of the system. It will be same for all the pulse type. And this is the displacement of the wall for different high velocity pulses of different maximum amplitude. You can see there. And this is the behavior for the maximum force vibration phase. And I think this will also work. Just quickly show you the slide. I can show the slide again, sorry. Can you see my screen now?
Not yet.
It says I can't share the screen.
Not yet. The screen
Let me just try to. There's an issue. I don't know why.
Maybe you can try to share your entire screen, what you are seeing on your
Yeah,
screen, you'll be able to see.
I'm trying to. You
Yes,
can
now
see
it
now.
is come. Yes, yes,
Yeah. Okay. So no more touching with the screen now. So that's the video I wanted to share, which made the problem. So this is a high-speed camera. It's capturing the movement of the wall with a high-speed pulse. And this is all the force vibration phase. You can see the deformation of the wall and the soil. And then we let the system settle down and then record the free vibration of the system. And these are, again, all the shaking table experiment results. And we observe the activity displacement of the wall, residual displacement of the wall. And and you can do as many tests you want to. And this is the amplification of the backfill pressure, how the acceleration along the soil layer height increases, and it is a region because of dedicated high displacement here. So I will be just showing you some other results, which is estimation of the shapewear velocity. So if you know the arrival time of the input wave at the base of the model, and you know the arrival time or the peak of the wave at the top, you just use this formula, which is distance divided by time, to get the velocity of the stress wave of the shear wave in the soil. And then this is for different maximum pulses. So this is also in those papers which I just cited. Now this is the final two slides. I wanted to make more focus here. So what is the purpose of the research? Why we did lots of testing and what we are going to achieve out of it? It's just the papers, or it is something, a new learning to the society? And the answer relies on these two slides. So first thing is, based on this physical model testing, not, it doesn't matter if they are in geotechnical engineering or in other area. We are trying to achieve an understanding between the industry and academia, how to correctly model the earthquake response of the retaining walls. And in the paper we published in 2021, give a complete guideline for industry, how to use a molecular model in Americas, whether you can extend it to simulate the post-yield behavior of the soil or not. And you can do that, but it has to be calibrated accordingly. And we give a complete guidelines for industry and to other fellow academians to how to model the seismic behavior of the walls or any geotechnical structures using very simple molecular models, very popular. But people even don't know what their is capability and how to use it properly. And got published in 2021. And then again, industrial output is we also gave very simplified equations, assuming that the wall is like a cantilever base restraint wall, and you can estimate its earthquake response using very simplified formulations. Then to get the assessment of its displacement during an earthquake. And this is the major outcomes like which industry is looking for. So it will be helpful for everyone who's trying to design a retaining wall but don't know how to find out the displacement of the wall when it's subjected to the earthquake load, or trying to model a finite element behavior of the earth retaining structures and don't know how to do it properly. So this is the industry focus outcome based on this physical model testing. And the last one is the academic output based on this physical model testing, which I'm using and most of the time in my teaching, and my other friends at UNSW also doing the same, and which we are trying to teach and train the students, both undergraduate students, including PhD students, to getting a good idea of geotechnical engineering. So this is assessment of my subject, which I'm teaching from last 4 years at UNSW. And there's an example of how we can use the learning from our physical model testing into the training and teaching of undergraduate or postgraduate students. So we have been given a slope which you have to stabilize using this retaining wall, and student will be given limited dimension, limited geotechnical testing results, some CPT, SPT test results with them, and then they have to come up with this combination of wall height, base dimension at the top dimension, and they have to put it here and then try to say like, okay, this is the wall dimensions, This is the peak ground acceleration which has been given to them, and then we teach them using a freely available Abacus student version. Anyone can download that. Any student, anyone can download it. It's 1,000 nodes. It is free, and it will do this dynamic time history analysis for you. And then they have to predict this and using the hand calculations, compare the results, write the commentary, and that will be the best achievement, in order to train the future engineers, in order to understand how to design a retaining wall for loading. So these are the closing remarks. So seismic inertial forces, as I shown you throughout our model testing, and during those damaging images can cause excessive deformation and damage of the retaining walls. The physical models are useful to study the seismic behavior of any structures. Shaking table testing can be constructed in-house, and it will be a cost-effective initiative. And the instrumentations could be very costly, but you have to plan them accordingly. What instrument is very crucial for you, how many you need them, and whether it's suiting your budget or not. That's all. Thank you so much. And now I'm open to the questions.
Thank you. Thank you so much, Dr. Tiwari, for your wonderful explanations and even giving an academia and industry both the focuses. So there are a few questions from our audience. First question I'll post is, how are the springs at the end designed to nullify the reactions from boundaries in your shake table?
Okay, so very good question. So I will just go to the slide and show you. So the springs
are on slide 28 was there maybe.
Yes. So the springs, if you can see, you see those boards there, right? And these heads, you can tight them or release them in order to, depending on what kind of density you are testing inside it. So if it's a very dense soil, you have to make them loose enough so that it won't reflect the boundary condition. If there's a very loose soil, then it's not that much problematic. But again, you have to check the reflection. So if you see here, we place the accelerometers on the boundary and at the middle as well. And we compare both the reading, how much reflection is coming back from the boundaries, so that you can adjust it accordingly.
One next question was there. What were the target results from the shake table tests?
So the target results could be... Yeah. So have you completed the question?
Yes.
Okay, so the target is depending on what you are testing. So for example, so if this is an embankment, right? So the target result, what we are trying to achieve here is how much liquefaction is happening and what is the PGA, what is the timing of the liquefaction, and then can we relate the timing of the liquefaction, okay, and the timing of the PGA. And we are writing a very groundbreaking paper at this stage. It's finally a PhD project right now. And we're coming up with a very good guidelines comparing the result of the shaking table experiment plus the CPT test plus we have our own calibration chamber here, which we can use for the saturated and unsaturated soil mechanics problems. And again, the outcome could be vary. So for the retaining wall, the outcome was what's the displacement of the wall, whether we can estimate the shear velocity using the accelerometer placed inside the backfill, and then whether you can use those results to calibrate the computer model. So that was the main outcome. And even it became input for the finite element models. So you have to plan according to what is the limitations. You can get a very complete picture or true model behavior using the scaled down models, especially in 1G models. So you have to be reasonable what it can show you or what you can get most out of it, and then how you're going to use it.
Yes. One more question was there. Were these results verified with theoretical calculations also? Along
yes. So with this paper, if you will see here, I'll show you this one here. So once you do the calculation, we also estimated the shear stress and shear strain, the soil elastic shear theory, and then so validations are there, but of course, the classical theories, they have their own assumptions. So they are having their own limitations. So we do validations, but it cannot be, so liquefaction, you don't have any validation for it. So it's just you record the pore pressure inside the soil, and when it hit the effective stress line or zero shear stress, that's your liquefaction. You don't need any theory. But what do you need for the theory is once you do the CPT, whether it correlate with the general available guidelines for the relation between the CPT and liquefaction or not. And we are trying to even modify their theories based on our own observation. That's the beauty of the experimental work, actually.
So these were the questions from the participants. If anyone has any other query, you can raise it now. Otherwise, it is lunchtime in India, as per our schedule. So thank you so much once again, Dr. Tiwari, for your elaborations and your research work, which is very extensive. And I hope in near future we can collaborate. Our students can get guidance from you. And we also have a 1D shake table in our premises, which we are using for structural testing. That is for 1000 kgs payload capacity. So it was very wonderful to see your work with your two-dimensional capable shake table and the theories which you are trying to modify with the results you are producing.
Yeah, thank you for having me. Thanks.
Thank you so much, sir. So to all the participants, for now, this keynote 1 and 2 address are done. So we will be again moving ahead with the program at 2:30. And at 2:30, we will be starting with our next two sessions, technical session 2A and 2B. And we will be having further keynote sessions 3, 4, and 5 scheduled from 2:30 to 5 p.m. So I request all of you to keep join on the same link for keynote sessions, and for technical sessions we have given links for virtual room CR 13, 14, 15 with your schedule of your technical presentation. You can please move ahead to the same. So once again, we thank all the participants and we thank our keynote speaker for having this wonderful discussions with us. Thank you so much. We'll meet back on the same channel at 2:30 p.m. Thank you.
Thanks.